Four resistors are connected. Then we have to find the potential difference Vc minus Vd. R1 2 ohm, R2 3 ohm, R3 4 ohm, R4 6 ohm, EMF 10 volt. We need the potential difference between C and D. Let I flows, let the current I1 flows, let current I2 flows. So by Kirchhoff's first law, I is equal to I1 plus I2. Applying Kirchhoff's second law to this loop, minus I1 R1 minus I1 R2 plus EMF equal to 0. So I1 is 2 ampere. By KVL in this loop, minus I2 R3 minus I2 R4 plus E equal to 0. So I2 is 1 ampere. Hence I equal to 3 ampere coming. In the path CAD, VC plus I1 R1 minus I2 R3 equal to VD. These two terms will cancel. So VC equal to VD. Vc equal to Vd. So if any resistance is connected between C and D, no current will flow through this resistor. Hence there will be no change in the current distribution in the circuit. Hence the effective resistance between A and B remains same and is independent of any resistance between C and D. Any resistance connected, the effective resistance between A and B remains same. Consider 5 resistors connected in the figure. Find the equivalent resistance between A and B. 1 ohm, 2 ohm, 3 ohm, 6 ohm. So this by this is equal to this by this. Hence this is the balanced Wheatstone bridge. So no current will flow through 5 ohm resistor if a battery connected between A and B. So this resistance can be removed without affecting the current distribution. Hence this circuit is equivalent to this circuit. These two are in series, the effective is now 3 ohm. These two are in series, the effective is 9 ohm. 3 ohm and 9 ohm are in parallel between A and B. So the effective resistance is 9 by 4 ohm. Consider 4 resistors connected as shown in figure. Find the potential difference Vc minus Vd. This is 2 ohm, this is 2 ohm, this is 2 ohm, this is also 2 ohm. EMF is 10 volt. Let I current flows, let I1 flows, I2 flows. By Kirchhoff's first law, I equal to I1 plus I2. By Kirchhoff's second law, to this loop, minus I1 R1 minus I1 R2 plus E equal to 0. So I1 is 2.5 ampere. By Kirchhoff's second law, in this loop, minus I2 R3 minus I2 R4 plus E equal to 0. I2 is 2.5 ampere. So I is coming 5 ampere. In the path CAD, Vc plus I1 R1 minus I2 R3 is Vd. These two terms cancel. So Vc coming equal to Vd. So if any resistance is connected between C and D, no current will flow through this resistor. Even if we can join a connecting wire C to D, through this connecting wire also no current will flow. So there is no change in the current distribution if we add any resistance or a connecting wire. Hence The effective resistance between A and B remains same for any value of resistance connected between C and D. Consider 5 resistors connected as shown in the figure. Find the equivalent resistance between A and B. 2 ohm, 2 ohm, this is 2, 2, this is also 2 ohm. So this is the balanced Wheatstone bridge. If a battery is connected between A and B, no current will flow through this 2 ohm resistor. So this resistor can be removed without disturbing any current distribution when there is a battery between A and B. Hence, this given circuit is equivalent to this. These two are in series. It is now 4 ohm. These two are in series. It is also 4 ohm. These two 4 ohm, 4 ohm, they are connected in parallel between A and B. So the effective resistance is 2 ohm. Consider 6 resistors connected as shown in the figure. Find the potential difference Vc minus Vd and Vf minus Vg. Let current I flows. This way I1 flowing, this way I2 flowing. So I must be equal to I1 plus I2 by Kirchhoff's first law. By Kirchhoff's second law, to this loop, minus I1 R1 minus I1 R2 minus I1 R3 plus E equal to 0. So I1 is coming 10 by 6 ampere. Applying Kirchhoff's second law to this loop, minus I2 R4 minus I2 R5 minus I2 R6 plus EMF equal to 0. So I2 coming also 10 by 6 ampere. In the path CAD, Vc plus I1 R1 minus I2 R4 equal to Vd. These two terms cancel. Vc equal to Vd. In the path FBG, Vf minus I1 R3 plus I2 R6 equal to Vg. These two terms cancel. So Vf equal to Vg. So if any resistance is connected between C and D or connected between F and G, there is no variation in the current distribution. Hence the effective resistance between A and B remains same for any resistance connected between C and D or connected between F and G. Consider 8 resistors connected as shown in the figure. Find the equivalent resistance between A and B. If a battery connected between A and B, no current will flow through the resistance R7. No current also flows through the resistance R8. So the current distribution will not be changed if we remove these two resistance. Hence, the given circuit is equivalent to like this. These three are in series. It is now 6 ohm. These three are in series. It is 6 ohm. These two are parallel between A and B. So the effective resistance is 3 ohm. This you will do by yourself. Consider 6 resistors connected as shown in figure. Find the potential difference Vc minus Vd and Vd minus Vg. Between this and this and between this and this, we need the potential difference. Each resistor is now 1 ohm. Let current I flows, then I1 flows, I2 flows, I3 flows. So by Kirchhoff's first law, I equal to I1 plus I2 plus I3. Applying Kirchhoff's second law to the closed circuit, this minus I1 R3 minus I1 R6 plus E equal to 0. So I1 coming 5 ampere. Applying Kirchhoff's second law to this closed circuit, minus I2 R2 minus I2 R5 plus C equal to 0. I2 is also coming 5 ampere. By KVL in this loop, minus I3 R1 minus I3 R4 plus C equal to 0. So I3 is coming 5 ampere. In this path C A D VC plus I3 R1 minus I2 R2 is VD. These two terms cancel, so VC equal to VD. In the path DAG VD plus I2 R2 minus I1 R3 is VG. These two terms cancel, VD equal to VG. So if a resistor or a connecting wire is connected between C and D, similarly if a resistor or a connecting wire is connected between D and G, there is no current in this path, also there is no current in this path. Hence, the current distribution is not affected by the presence of any resistance between C and D or any resistance between D and G. So the effective resistance between A and B remains same for any value of resistance connecting CD or connecting D and G. Each resistance is 1 ohm. We have to find the effective resistance between A and B. From the previous problem, we know if a battery is connected between A and B, no current flows through this R7 and also no current flows through this R8. So these two resistances can be removed without affecting the current distribution. Hence the circuit is equivalent to like this. These two are in series, it is coming 2 ohm. These two are in series, 2 ohm. These two are in series, 2 ohm. These three are in parallel between A and B. So the effective resistance is 2 by 3 ohm. This problem you will solve by yourself. This also you will solve by yourself. Consider 7 resistors connected as shown in figure. Then we have to find the potential difference between A and B. Also we have to find the potential of A and B related to the potential of A and B, and find the effective resistance between A and B. Let current I flows, this way I1 flows, let I2 flows, then this way I1 minus I2, I1 minus I2, then by Kirchhoff's first law I1 flows. This way current flowing I, this way flowing I1, this way also I1, this way I2, this way I1 minus I2. In the path AB, VA minus IR is VB. In the path AA, VA minus I1R minus I1 minus I2R is VA. In the path AB, VA minus IR minus IR is VB. In the path AAB, VA minus I1R minus I1 minus I2R minus I1 minus I2R minus I1R is VB. From this equation IR is VA minus VB. Let us put this IR in this equation, so becomes this equation. Hence VB coming VA plus VB by 2. Similarly VA coming VA plus VB by 2. So there is no potential difference between A and B. If a resistor connected between A and B, or a connecting wire is connecting A and B, there will be no change in the current distribution. Hence the effective resistance remains same for any value of resistance connecting A and B. This R, they are in series. The effective resistance is 2R. These two are in parallel with R. The effective resistance is R1. This R1 is in series with R and R. So the effective resistance is R2 is R1 plus 2R. This R2 is parallel with 2R. So the effective resistance is 16 by 14 ohm. This you will do by yourself. Consider 7 resistors connected as shown in the figure. Find the equivalent resistance between A and B. The given circuit is equivalent to this. We know from the previous problem, if a battery is connected between A and B, no current will flow in this wire. It is now a connecting wire. It may be a resistor also. So this AB joining part we can remove without affecting the current distribution. Hence the given circuit is equivalent to like this. These two are in series and then it is in parallel with R. The total resistance is now R1. R1, RR, they are in series and that is in parallel with 2R. So R1 is 2 by 3 ohm. Then effective resistance is coming then 8 by 7 ohm. This you will do by yourself. This also you will do by yourself. This one you will try. Consider 5 resistors connected in the figure. Find the equivalent resistance between A and B. This R1 resistance is in parallel with R2. How do you know? You can cut here and this point you can touch here. Similarly R1 and R2, they are also in parallel. You can cut here and you can touch this point here. So the given circuit is equivalent to like this. These two are parallel. It is now 2 ohm. These two are parallel. It is also 2 ohm. Between A and B, these two are in series. It is now 4 ohm. This is 4 ohm. This 4 ohm, they are in parallel. So the effective resistance is now 2 ohm. Consider 6 resistors connected. Find the equivalent resistance between A and B. B point can be considered to be any point on this line. Similarly, point A can be considered any point on this line. So, this circuit is equivalent to this circuit. This 2 ohm, this is now 2 ohm. It is connecting A and B. These 5 resistors is now forming the balanced Wheatstone bridge. So this is the balanced Wheatstone bridge. This 5 ohm is this one. This 1 ohm. This 2 ohm. This 2 ohm. This 4 ohm. This is the balanced Wheatstone bridge. So this means this we can remove without affecting current distribution when there is a battery connecting A and B. So this circuit is equivalent to this circuit then. 1 ohm 2 ohm in series, it is coming 3 ohm. 2 ohm 4 ohm in series, it is coming 6 ohm, and this is 2 ohm. These three are in parallel between A and B. So the effective resistance is coming 1 ohm.